Hello everyone, this is my presentation on time complexity for Comply 123 by Michael Vincent Lozado. So our topics for today about time complexity, we're going to discuss algorithms, program, runtime, the RAM model, the big O notation, and asymptotic notations. So what is an algorithm? So it is a finite set of instructions to do something or to solve a problem. So to understand more about it, so we have our example problem or activity, which is preparing for school. So what an algorithm is step 1, you wake up, then step 2, you fix the bed, then step 3, you take a bath, then step 4, you eat breakfast, step 5, you read your book, then step 6, you answer questions. So it's the same with cooking fried eggs. So step 1, you get the eggs from the fridge, then you prepare your pan, then you light the stove, then you put the oil, then you crack the egg, then you put the egg in the pan, then you add salt for flavor, then you wait for the egg to cook, then you put the egg in the plate. So that is it. So an algorithm is a set of instructions to do something. So that's your algorithm to prepare for school or to cook a fried egg. Next, we have program. So a program is a group of code that contains the algorithm. It is an instance of an algorithm written in some programming language. So one algorithm below could have many similar programs. So example below are two programs with the same algorithm. So our algorithm here is to find the sum of the set of numbers. So in our example here on the left, which is also a program, a Python code. So the sum of numbers here in a set of numbers. If you get the sum manually, then the sum here will be 55. So this is our program to get the sum. And in the right side, it is a Java code, Java programming language code. We're taking also the sum of the set of numbers. Alright, so we have our running time. So what is the running time? So it is the time it takes for the program to finish. In computer science terms, it is the time to execute a code. So in our example, I'm going to ask you if you have ever tried watching a cartoon series or anime series on TV. So if yes, then the time it took to finish the series is your running time. For example, you started watching Avatar, The Last Airbender series. So let's say you started watching on Monday, and you plan that you're going to watch one episode every day. So there are 5 episodes in season 1. Let's just assume, let's say, that on Friday you finished watching all 5 episodes. So what is our running time here? So as we said, we watched one episode per day. So one episode on Monday, one on Tuesday, one on Wednesday, one on Thursday, and one on Friday. So our running time all in all is 5 days because you had one episode per day. So you watched one per day from Monday to Friday. So all in all, 5 days. So it took you 5 days to watch all 5 episodes. But there are many things that affect the running time. First, it could be how much or less the items you're putting in your program, the input size, or let's say how many episodes you're going to watch, how the program code is created, the input structure or content. So the green one are computer science terms. So one thing that could affect the running time is the memory of the computer, or it could be old or a new computer, and the programming language used, and how many steps your algorithm has. So in our previous example, when preparing for school, we had 6 steps. So it could vary, it could change. So other people might have 3 steps, or 9 steps, or 15 steps. So it could really change. So just like when you're watching The Last Airbender, if it took you 7 days, or just let's say 5 days, because that was our running time. So if let's say you had 5 days to watch all the episodes, well, maybe because you had to stop watching because you did other things like sleeping, eating, playing, or doing your homework, diba? So it could vary. Could be running time could be just like 2 days or 1 day because if you really watch all 5 episodes in 1 day, no. But then you watched one episode per day long because you had to sleep, of course you had to eat or do your homeworks. So since it is hard to tell what the real running time is, we're going to ask what is the running time. So instead of asking what is the running time, it's better to ask what is the growth of the running time as the amount of input is increasing. So an example to you about watching Avatar: The Last Airbender series, a running time is the amount of time you took to watch all the episodes. So since our input is increasing, which means it is having a new episode. So the growth of the running time, let's say you have 5 days, and let's say there was a new episode. So since you watch one episode per day, so that's equal to 1 day for one new episode. So 5 days plus 1 day for new one episode. So more episodes means more days to watch all the episodes, which also means you are going to have a longer running time. So now time complexity. We're going to discuss time complexity. So it is an idea connected to algorithms. It is how fast and memory saving a program is. So there are three things to know. First is the RAM model, the big O notation, and the asymptotic notations. So we're going to discuss about the RAM model, which is the random access machine model. So it is this one right here. So it is a simple computer model. It has things a computer also has, which is memory, input, and programming capabilities. So in a RAM model right here, we have what we call the RAM memory. So it is divided into separate boxes or cells. Let's just call it boxes. And these boxes have limited capacity, and it can have as many boxes. You can have as many boxes to store your memory, just like in our visual representation right here. Each box is only has a limited capacity. You can only, let's say, store one letter, just A, B, C, D here, right here. But you can have as many boxes to store all your memory. You can have unlimited boxes to store all the letters you can think of. So in a RAM model, we have what we call the RAM time. So we have the RAM analysis, which is we are going to take the number of time steps. So since this is time complexity, so operations like adding or subtracting take one time step. We are measuring the time steps, the time complexity it has. So assigning steps take like A is equals to 1, take 0 time steps. For example, right here, in line 1, we assign S to 0, which has a 0 time step. And on line 2, we have the while method, which is a loop. Then inside our parentheses, if the S is less than 5, so it's comparing, so it is an operation. And in our third line, if S is equals to S plus 1, and S plus 1 is one time step, but the assigning is 0, so it's just one time step. So since our S right here is 0, so it will first compare S0 to 5. Since it is said that is true, then it will proceed to the third one. So 0 plus 1 is 1, then our S is now 1. Then we will compare again. 1 is less than 5, which is true. So it does what? So this is what it does right here. So it compares 0, then 1, then 2, then 3, then 4, then 5 to 5. It compares 6 times. It is thus comparing 6 times. Then in our addition right here, it also adds 1 to S 5 times. So in all, we have 11 time steps. So next we have our big O notation, which is the worst case growth rate, or the upper bound. So since we have many kinds of cases, we have the best case and the average case. So the worst case is the most recommended because nothing can be worse than a worst case, right? So what you can do with the worst case is just you make it better, unlike the best case and average case. It can get worse than that, so it's not reliable. So this type of notation focuses on the growth rate of your running time. So let's say n is your input size. So as your input size n grows, what happens to your running time? So we have examples of a graph right here with the big O notation. So as our input size increases, the running time also increases. It shows how the running time, the growth of the running time is increasing, or what is its behavior of the growth. So in a big O notation, having a slow growth is a good one, which means your program is good, your time complexity is good. And if you have a fast growth, then it's a bad one. Then examples right here are previous ones. So this kind of growth right here is the O of n, or the big O of n type of growth rate. So it's just a straight line. You can also call this a good one. Then we have O of n squared. It's a quadratic growth rate. So as you can see here, as the growth rate, input size, increases, the running time is greatly increasing. So the growth rate is kind of steep. So we can call this as a bad growth, a fast growth, which is a bad one. Then we have O of log n, or O of logarithmic n, just like that. So that is its behavior. So in a mathematical definition of the big O notation, so we have two functions, f of n and g of n. If it grows faster than, if g of n grows faster than f of n, then we have two rules. If there exists a number m and a constant c, such that c times g of m is greater than f of m, and we have a second rule, which is for all numbers of p, which is greater than n, we have g of p is greater than or equal to f of p. For example, right here we have two functions, f of n and g of n, and we have our numbers m is equals to 3, c is equals to 2, and n is equals to 1, and p is equals to 2. So if we substitute the value of m right here, then c or here is 2, then c times the function g of 3 is greater than or equal to f of 3. So since g of 3 is 14, so 2 times 14 is 28, and f of 3 is 10, so 28 is greater than 10, which is true. Then for our second rule, for all p greater than n, so 2 is greater than 1, so we substitute p here in our function. So f of 2, 2 times 2, 4, plus 4, 8, 2, 3 times 2, 6, plus 5, 11. So g of p, which is 11, so it's greater than 8, which is true. So we can say that f of n is contained in big O of n, big O of g of n, sorry. So these are the different kinds of big O notation. We have the O of 1, is the fixed number, so it's somehow the best kind of big O notation there is. Then we have the O of n, the green one. Then the O of log n, the yellow line, the yellow growth rate. Then we have O of n squared, which is somehow a bad type of growth rate. So we can see here is purple line having a steep growth. Then we have what we call the O of 2 raised to n, or the exponential growth rate. So this is somehow one of the worst kind of growth rate you should avoid when creating your programs. So we have our asymptotic notations. We have the big O notation, which is the worst case growth rate, the upper bound. We also have the big omega, which is the best case growth rate, as mentioned earlier. The lower bound, we have the theta, the average case, the little o. Of course, if there was a big O, then there's also a little o. Then this is a smaller version of the big O notation. It is also an upper bound, but not exactly. So it's not an accurate type of notation. So it's the same with the little omega. It's the smaller version of big omega notation. A lower bound, but not exactly. So it's not accurate. Alright, so thank you for listening, and I hope you understood the concepts of time complexity. And so have a good day. Thank you very much.